So we want to do a case study. Okay, so I also linked the paper on course website. You can actually, actually click it and try to read that paper. And I promise you that the paper is actually not super hard to read based on what you have learned so far. Right. Okay, so this is the program, and we have already seen, what happened. This program is capable of beating, the world champion at that time. So we're gonna go through the older version of AlphaGo, not the latest version that beat the current best player in the world. Right? But this older version was pretty strong already. It basically beat the legend of this Go game, right? This Korean professional player. Okay, good. So the outline for today is, let's talk about the setting. So this is slightly different from the Markov decision process that we talk about, right? Because this game has 2 players. So far we only looked at the Markov decision process where we only have 1 player, right? And then we will see how they warm start everything using imitation learning, and then how they keep improving the policy using policy gradient. Right? And the last step is that you combine this policy, a value function estimation, and a search tree algorithm together. Right? So after all, this is a game where you know everything about the state, the action, the transition dynamics, right? You put a stone on this board position, the next state is a trivial next state, right? So you know everything about the dynamics, so you can technically just do a tree search, right? But we will see that how we can use a policy and a value network to significantly reduce down the search space, so that we can do it still. We can still, use a tree search algorithm during the real-time play. Okay, so here is the setting. Okay, sorry, there's some lag on my slides. So let me just stop sharing and redo it again. Okay, great. Okay, so this is the Markov decision process that we talked about, right? So we have state action. So here I'm using F to represent the transition, because we're just gonna focus on deterministic transition, right? There's no stochasticity in transition. You're at this border position, you play that piece and you get to the next state deterministically and trivial, right? The transition is trivial. So let's just write S prime equals to F SA. Right, so we have a reward function R, we have finite horizon H, and we have a fixed initial state S0. All right, so this H is, let's say this is an upper bound of the total number of steps that this game can last, right? So this thing can vary, depends on the place, because sometimes the game just ends early, right? But let's just, for simplicity, let's just assume we have some upper bound, capital H on that. Okay, so in this game, we have 2 players, right? It's not, a 1-player game, right? It's not like you're playing a video game, right? So this is, you have 2 players, pi 1 and pi 2. And a game needs to be played by both of them, right? So the way that the trajectory is generated is that we start from the initial board position, then player 1 started playing action, right? So player 1 picks A0. This is player 1. Right? And then once it plays this action, we transit to the next state deterministically, right? We get to S1, and now it's the turn of the second player, right? So then second player comes in, it makes a decision, uses its policy, and then we move on to the next state, and so on and so forth, right? So every step, only 1 player, at every time step, only 1 player is making the decision, right? And then they take turn. And they play this game many, many rounds until they hit a final state, a terminated state, as H. Right? So
isn't the policy also deterministic?
That the deterministic is fine. Deterministic, think about the deterministic as a special case of stochastic.
Okay.
Right. Okay, so that's how the game is played. And we're going to assume sparse reward. We're not going to do any reward engineering. We're just going to use the reward function, which is at a terminated state, you win the game, you get rewarded 1. You lose the game, you get rewarded -1, right? That's the most natural reward design that you want to do. Okay, so we have this min-max formulation, right? So because this is a 2-player game, right? So this is not just maximizing the policy with respect to the expected total reward. So this is player 1 is trying to maximize its own winning rate, right? So this is, oops, sorry about that. So expectation of the reward is the winning rate for player 1, right? So player 1 is trying to maximize the winning rate, while player 2 is trying to minimize player 1's winning rate. So this is what this min-max is doing. Right, so you're trying to maximize the winning rate, but your opponent is trying to minimize your winning rate, right? So there's a max-min procedure here. Okay, so as usual, even though we're dealing with 2 players, we can still define the optimal value function. Right, so let's define V star S as the max-min value of the game if we start at state S, if we start playing at state S, and if both players are playing their perfect strategy. Right, so this is the max-min value of the game if we start at state S and every player is playing the perfect move. Right, so this is the game. Let's call it the value of the game. Yeah, so basically this is the optimal game value if you start at S and both players plays optimally, right? Imagine we solve this min-max problem, max-min problem. Both players are using their optimal policy, right? They start at state S, and what is the expected winning rate for player 1, right? So that's the value V star. Okay, so this is a zero-sum game in the sense that both players, they cannot both win or lose, right? So one player wins, one player loses. So the total reward of this game, the total sum of the reward of this game is 0, right? One player get rewarded 1, the other player get rewarded -1. So the sum is always is 0. So in other words, they cannot both win or lose, right? So that's just by the rule of the game. So this is called zero-sum game. Right, so you can think about player 2. Player 2 tries to minimize the expected winning rate of player 1. So in other words, because this is a zero-sum game, this means that the player 2 is actually maximizing its own winning rate, right? Because you just negate the value. So player 2 is trying to minimize the expected winning rate of player 1, but this is a zero-sum game, right? So if you minimize the player 1's winning rate, you're maximizing your own winning rate. Right? So that's the property of the zero-sum game. The common games such as rock, paper, scissors is also a zero-sum game, right? So we cannot both win at the same time. Okay, so this is roughly the setting. We're not gonna spend too much time on this two-player Markov game because this is sort of more related to game theory stuff if we keep talking about this zero-sum game. But the bottom line is that this is a zero-sum game. The optimal strategies exist, right? So you can solve this min-max if you have enough computation. You can solve that. The optimal strategy exists, right? The solution to this max-min problem exists, right? So this we call it a Nash equilibrium. Okay, so we have this min-max formulation. As I said, this is a zero-sum game. The max and min solution, the optimal solution to this max-min optimization problem exists. And the way we can compute this is actually using dynamic programming, right? So, for this particular game Go, it has known and a deterministic dynamic, right? The dynamic is very simple, like based on the board position, based on the action, like the next state is trivial, right? Like everything is known. There's no hidden stuff in this game, right? So in other words, we can actually use dynamic programming to solve this max-min formulation. Right, like if we don't worry about the computational space, whatever, information theoretically, we can use the known information, the known dynamics to solve this game using dynamic program, right? So this will be very similar to the value iteration or the dynamic programming stuff that we did for AOQR. Right? But there's a big but for this game. Right? So the game roughly has h equal to 150, right? So the game in average probably lasts more than 100 steps. And roughly the number of actions you could play per position is around 250. So, which means that the total number of possible moves you could have in this whole game is this a to the power of h, right? I didn't even bother to calculate this number, and this number does not gonna look good, right? So which means that we cannot just do dynamic programming. Like we can't even write down the full loop for this state, right? Like you won't be able to finish, one pass. Like you won't be able to finish the full loop, and we don't even have spaces to do that as well. Right? So this really means that we cannot enumerate, right? Dynamic programming requires to enumerate, right? Because you need to record down, the value for different state, right? And then you can do dynamic programming based on the information that you recorded down so far. So this means we cannot do that. We must generalize via function approximation, right? So in the training time, we will not be able to see all possible configurations. That's just not be possible, like space-wise and computation-wise, no way, right? So we have to generalize in the sense that we have to, based on the finite number of examples that we have seen during training time, to generalize to the potential configurations that we could run into during a play, right? Those test configurations during a play might not even show up in the training time. So we have to be able to generalize in order to do well, right? Relying on a pure search algorithm is not really going to do that well for this game because of this giant search space. Okay, good. So the way we're going to do that is use a function approximation to approximate the policy. All right, so this is what we have been doing, for policy gradients, right? So we're gonna have this policy net, of which the goal is to approximate the optimal policy, the optimal play, right? So the policy basically takes this border position. Just think about this border position as an image, right? It has probably two channels. Each channel corresponds to a different color of the stones, right? And you probably append another channel to the image, which is a channel indicating which player is played. It is the first player or the second player, right? So basically you can encode the information about the whole game, the game at this stage, into this image, right? So that's called state S, right? And what you do is just feed this image to a convolution neural network, right? So the convolution neural network they used is pretty standard. I don't think there's a very special stuff in their network design, right? So this is just multi-layer convolution neural network, those convolution neural network that you would use for image classification. All right, so the output of this neural net is a distribution over actions, right? So this is pi dot given S. So this is a distribution over all possible movement that you're legally to do at this moment, under this state, right? So this is just a usual policy parameterization. Right, so this is a convolution neural network. This is a differentiable policy. Another network we're going to use is a value network. So this value network is trying to approximate the game value, V star. So given a state as prime, right, which is a border position again, what is the winning rate, if both players play optimally? So that's trying to use another function approximator, in this case, another convolution neural network to approximate this value, right? So this network will take this border position as an image, as input, go through multiple layers of convolution, and then outputs a scalar, right? Our goal is to try to train both network to achieve their goal. The first network's goal is to approximate pi star. The second network's goal is to approximate V star. Right? So that's the function approximation setting. We're only going to use these two function approximations. Okay, great. That is the setting. Any questions about the setting? So we just very quickly talked about the two-player Markov game, and also the policy parameterization and the value network parameterization. Okay, great. So let's talk about the second component, the imitation learning component. Right. So because this is a well-studied, this is a very popular game in Asia, right? So people have, recorded it or logged it down, those movements, those plays. So what they did is that they warm start our policy net via imitation learning. So that seems a very reasonable strategy to do, right? Like why don't we, why should we start from a random stuff, right? If we have expert data, let's start by using imitation learning. So they randomly sampled an expert data set containing 30 million state action pairs from this, whatever, KGS Go server, right? So that's what they did. You just get a bunch of random plays from those high quality games, recorded high quality games. So think about this as the expert state action pair, right? So recorded imitation learning lecture. We have a data set from expert, right? And they're not even using fancy imitation learning stuff. What they do is they just form an imitation learning loss function. In this case, they use a negative log likelihood, right? So which means you're trying to find a policy pi that maximizes the likelihood of generating these expert action, right? So this is expert action, right? So we are minimizing the negative log likelihood, meaning that you're maximizing the log likelihood, right? So you're trying to find a policy pi such that the probability of playing the expert action is pretty high. So that's the goal, right? Okay, so you have this well-defined objective function, right? And what they do is actually just optimize it by stochastic gradient descent, right? Nothing fancy here. What I'm doing is just randomly sample a mini batch from this 30 million, state action pairs, right? And compute the gradient of the loss function for each sampled state action pair, sum them together, divide by the total number of samples in the mini batch. So this gives me an unbiased estimate of the gradient. Right? And then let's just do gradient descent on the parameters of the policy. Right? We do gradient descent until things are converged. So what does what is this algorithm, right? So this is the simplest behavior cloning algorithm that we talked about at the very beginning of imitation learning lectures. Right? Nothing fancy. We're not using the interactive dagger learning setting. We are not using this like max and inverse RAO setting. We're just doing this behavior cloning. Okay, great. So we trained that on this big data set until it converged. So what's the performance? So first thing that they tested is, let's test it on a holdout expert test data set, right? So I have 30 million state action pairs. Maybe I just split it into training and test. I train it on the training part, and I'm gonna test it on the test part, right? So let's see, what's the probability of what's the accuracy of predicting the expert action at a holdout test set. So the accuracy is actually not that high. It's 50%, 57% accuracy on the holdout expert data set. It's also not a bad number because the number of actions here, right, is around 200. So you're doing like 200 multi-class classification. This is not a binary classification, right? So a random strategy, what's the accuracy of a random prediction strategy, right? It's like 1/200. So in this sense, 57% accuracy is definitely non-trivial, right? So this is the test accuracy on a holdout test set, right? But what would happen if we play this policy in a real game, right? What's the winning rate? So what they did is that they test this against an open source Go program. And the winning rate that they got is 11%. So not too bad. I mean, this is a non-trivial open source Go program, right? So like what we have done so far is just the most naive imitation learning algorithm, right? We just collect a bunch of expert data set and we run like behavior cloning. We run like gradient descent on the negative log likelihood objective function, right? And we're leveraging the power of deep neural nets. So that's the only, advanced stuff that we're using. Other than that, if you remember, right, behavior cloning, we talked about that self-driving car example, right? CMU folks were using behavior cloning for self-driving car like around 1989. So algorithm-wise, there's nothing new here yet. Okay, so this is 11% winning rate, not too bad. And let's see now if we can improve this winning rate by using reinforcement learning strategy. So far, we have not used the reward signal yet, right? We're just mimicking an expert. Okay, so let's see now what we can do in the reinforcement learning component. Okay, any questions about the imitation learning part? Okay, so let's see how we can further improve in the policy using policy gradient via this thing called self-play. Again, this is a two-player game, right? So in order to simulate the game, we need to have two components, right? Player one and player two. So the way you're going to simulate the game is you're just going to constantly play against yourself. So we're going to warm start our policy gradient procedure using the policy trained from behavior cloning, right? So we have a reasonably good policy. So let's start from there, right? Let's not throw away the information that we got from behavior cloning. Let's just start from the parameter that is outputted by the behavior cloning. And let's start gradient descent from there. Okay, so then we iterate as follows. So we're just going to do policy gradient updates here. Okay, so every iteration we compute a policy gradient of the current policy and we do policy gradient update. So more formally, let's start from this is warm. Let's warm start from this initialization, right? We initialize our policy to be the output of the behavior cloning component. Right, that's our initialization. It's not a random initialization anymore, right? So this is a warm start from behavior cloning. Okay, so then for t equal to 0 to capital T minus 1, we first going to randomly select an opponent to play against. So the way that we do this is to randomly select a previous policy that we learned so far, we stored so far, right? So this tau is an iteration that is less than the current iteration. So we have trained many, many policies, right? So let's randomly pick a previous policy as our current iteration's opponent. Right, so this is a thing called a fictitious play in game theory. And the reason that we want to do that is to avoid catastrophic forgetting, right? So we don't want to forget how to play against an older player. Right, so if you randomly, sample an opponent from all the policies that you have computed so far, you will be able to learn a policy that actually do not forget about how to play against, an older opponent. And now we're just going to play the current policy pi theta t against the sampled random opponent, right? And the way we play the game is just let these two players. So this will be my player 1. This will be my player 2 at this moment. Just let these two players play against each other, right? Starting from S0, we sample action A0 from pi theta t. And then we move one step forward. And now player 2 plays this. And now so on and so forth. Every player take turn until we hit the final state, right? This is a terminal state. Okay, so we just let them play and we get a trajectory, right? So let's use our, the simplest policy gradient formulation that we learned so far, right? So this is just the reinforced formulation. So what are we doing, right? So we just use the final reward, right? Because this is a sparse reward setting, right? So we get a reward signal at the end of the trajectory. So RS capital H is essentially the total reward across this entire trajectory, right? Because All the previous time steps has reward 0. We only get a reward signal, +1 or -1 at the end of the trajectory. So this R as capital H is essentially the total reward across this entire trajectory, right? And then we just sum over different time steps that corresponding to player 1, our policy, right? So this is a time step corresponding to the time step where player 1, our current policy plays. Right? And then we just compute the gradient of the log likelihood of our policy. So this is just the reinforced formulation. Right? We're not even using fancy, natural policy gradient stuff, right? We're just using the very simple reinforced formulation. Okay, and then we do gradient ascent because we're maximizing the reward, right? And then we repeat until it converged. Okay, so that's the algorithm. Very simple. The only is probably this step, right? So they must have tried to replacing this step by just asking the current policy to play against the current policy. That potentially causes instability issue during training. Potentially the policy learns to beat itself, but forgets the strategy about playing against the older version of itself, right? And then they probably switch to this fictitious play.
So the previous policies, does that include the behavior clone policies?
I think so, yeah, because this is pi theta 0, right? Behavior cloning policy is pi theta 0.
Oh, I see. It's only counted there. It's not like many versions of behavior cloning.
No.
Okay, thank you.
So is it like uniformly randomly sampled across all the different?
Yeah, based on what I could find on the paper. Yeah. Okay, so the high-level goal here is to use policy gradient to improve our policy, right? The performance of our policy by playing against itself. Okay, so this is the algorithm for policy gradient. And as you can see, the policy gradient formulation itself this is a very simple reinforced formulation, right? So similar to behavior cloning, this reinforced formulation was invented probably 30 years ago. I think it was invented around 1993 by some other folks at CMU as well. So far, this program has been using 2 algorithms that are developed 30 years ago, right? Except that it's using deep neural nets, which is more modern. Okay, but other than that, the algorithm, the behavior cloning algorithm, the reinforced algorithm, they were invented, 30 years ago. Okay, so that's the policy gradient part. So let's just do policy gradient, until converge. And the question is, how does the performance improve, right? After PG optimization. So again, they tested it against this open source Go program, right? So the performance is increased all the way to 85%. So remember, BC only gives you 11% accuracy, right? So you significantly increase the winning rate by actually doing policy gradient using the ground truth reward of this game, right? Remember, behavior cloning is just mimicking. It does not even know that you're playing this game, right? It does not even use the game property, meaning the reward function. So now we optimize the ultimate objective function using policy gradient, and we significantly boost the performance from 11% to 85%. At this stage, this program is already very strong, right? But this is not strong enough to beat human champion yet. But it's pretty much, at this stage, it's pretty much, the strongest program already, comparing to the previous open source, programs. Right, so far, everything is just learning based. We haven't used search strategy yet, right? Remember, this is a game where we have full information about the game, right? Technically, you can use search tree, right? But we haven't used the power of search yet. So far, everything is learning based. So it's pretty remarkable that, forgetting about the search process, right? We can actually do that well just using simple gradient update. Like so far, we haven't even leveraged, the fact that we know the game, we know the dynamics of the game, right? Like we're just treating this game as a black box game where we don't know the dynamics, right? We just collect a bunch of data, do behavior cloning, and then we just run policy gradient. So now let's see if we can further make this program stronger by integrate a search component into this learning component, right? So this program is a good example of traditional AI approach, those search-based algorithm, right? Tree-based, search-based algorithm, and modern machine learning algorithm together, right? So like they're both gonna play together, and they're gonna make this program very strong, right? If you throw away one component, you will not do that well. Okay, so let's see how we can combine policy value. We haven't talked about value network yet, but let's see how we can combine policy network, value network, which we'll talk about in a second, and a search tree together. Okay, so the final stage of the machine learning part is just to learn a value function. So our goal is to learn this function v hat that approximates v star, right? But v star is really hard to approximate because remember, we will not be able to compute the optimal policy, right? So what they did is that they just aim to learn a function approximator that predicts the value, the game value of the policy gradient policy pi hat. So imagine now we're done with policy gradient right now. Okay, so we're not going to go back to further polish our policy. So policy gradient is done. So we outputted this policy pi hat. So this is the policy outputted from policy gradient. And now what they do is just learn the function approximator to approximate the game value of this policy. Meaning that starting at S, if both player plays pi hat, what's the winning rate of the first player? Right? What's the expected total reward of the first player if both player is playing this pi hat? Right? Of course, this is not going to be close to V star, but hopefully this gives us a reasonable estimation. And when we combine it with search tree, the sort of the approximation error could gradually vanish if our search tree has really long, really big depths. Yes, question?
Shouldn't this be 0 if you're playing it against itself?
Not really, right? It depends on your state. So I'm not sure if the game if you will get 0 at the initial border position if you play against yourself. But at different state, it will have different value, right?
Yeah, I think, that makes sense.
Okay, so the way that they do this is, again, the simplest approach, least square. All right, so they just constructed this least square loss function. So the way you do that is you generate a bunch of state by playing pi hat against a pi hat, right? So you simulate many plays, many games by playing pi hat against a pi hat. And among these games, you pick an state and the value of the game, right? Which is Z. This is the value of the game. This is a state from the game. All right, so remember the goal. What's the goal? The goal is to try to predict the value of the game if both players are playing pi hat, right? So we're just gonna generate data sets using this procedure. Let two players play against each other using pi hat. And then we just select a state from that game and record on the value of the game and then form this least square regression problem, right? So here beta is the parameters of the value network.
What is the benefit to learning this value network then? Because if you're training it against the output of your other network, why do this?
Yeah, you will see it in a second. So you need to use that to cut the search depths of a search tree. Okay, so S is a random state in one game play, and Z is the outcome of the play, right? So here, one interesting thing that they mentioned in the paper is that they actually just keep one sample per gameplay. So in other words, they're really trying to do this ID sample from a policy's state action distribution, right? Remember we talked about how to sample a state action pair in an ID fashion from this D head pi, right? We talked about how to do rolling in, you randomly sample and time step, rolling in until that step, only keep the state at that time step, right? Throw away all the state away. So the reason that we said that we do that is to ensure IDness, right? But in the homework, we tried something different, right? We said that instead of just keeping a particular state action pair per trajectory, let's keep every state action pair. Let's just treat them independent, right? So that gives us a trade-off between, maintaining the IDness of the data and also the size of the data set. But in the paper, what they said is that actually just keeping one sample per gameplay gives the best performance. Well, so the reason is that they really trying to simulate this ID sample procedure from this distribution, right? You don't want to keep two states from the same gameplay because they will be correlated, right? So what they choose is just randomly pick one state on this game and just keep that state. That's it. Now, the reason they can do that is because this is a game, right? So you can actually simulate many, many games without any cost. The cost is probably burning some electricity. That's it. Right? So in other words, they don't really care about sample complexity too much, right? So you just want to get, the IDness. They just want to get the IDness so that their training process could be successful. Okay, so the way they collect the data is just self-play using pi hat and a pi hat for 30 million games. And now you get 30 million SD pairs. Right? Again, you get a state from each game and you record down the value of that game. So that's the data set you get. This is a very simple supervised regression data set, right? And then you just do stochastic gradient descent on the least square objective function, right? So remember the objective function is V beta minus C, right? So again, you just do a mini batch sample from the whole data set, compute the gradient of each state sampled state and Z pair, take the average. That's your unbiased estimate of the gradient of this least square loss function, right? And then the gradient descent. Okay, so that's basically the way that they train the value network. Again, they use very simple stuff, right? Least square regression and stochastic gradient descent. Yes, question?
So the state that they sample from each game, is that the initial state or do they?
No. This is randomly sampled.
I see.
Right, because your goal is to predict the game value from different kind of state, right? Not just the initial state.
Yeah.
Right. Yeah, so let me emphasize this. This is randomly sampled. Okay, so now we have policy net, we have value net. Okay, so the machine learning part is done. Okay, so we're not gonna, after this slide, we're not gonna do machine learning anymore, right? So we're gonna see how we can incorporate those traditional search algorithms from AI, to make the program even stronger.
So could you get better performance by actually running like the same training on the value function again, but with whatever policy you get out of this at the end?
So you were suggesting that we repeat the policy gradient again using the learned value function?
Or like repeat, like whenever we get to the end of this, then we have like, the best policy that's like the one that's capable of like beating like the champion Go player. Then can't we use that to get like to approximate the value function again and then like train again?
Yeah. But remember when we train the policy gradient component, right? We're not using any value function at all. So we're just doing gradient descent. We're just using the most simple reinforced formulation that does not using value network.
Right.
Right. So yeah, I mean, of course you can compete, you can repeat, right? Probably you can do more SGD and get the policy performance get even better. But the way that they're training the policy is that they're not using the value network for training the policy. Right. So I think what they were trying to do is just use this trying to use the simplest approach, as simple as possible. So they don't use this natural policy gradient. They don't use this actor-critic formulation that we saw as well. Okay, so everything is very simple so far. Like nothing is really sophisticated yet.
Had those techniques like not been invented yet?
No. I mean, this paper was around 2016, right? All this like actor-critic stuff, natural policy gradient was already invented. So again, they trying to get a very very good policy, but they don't worry too much about sample complexity, right? Because they have computational resources. They can simulate millions and billions of games inside their computers. So they're using thousands of CPUs and hundreds of GPUs to train this thing. Okay, so they don't worry about sample complexity too much. They just want to use the simplest approach and gradually improve the performance of the policy. Right? That's their goal. Their goal is just train a very good policy. And they don't worry too much about computation and sample complexity. Okay, great. So far we have learned this policy net from the combination of behavior cloning and policy gradient. And we learned the value net that approximates the game value of the policy pi hat. All right, so now let's see how we can combine this with a search tree. So let's just start from a very naive search tree procedure. Right, so imagine that we are at state S right now, and then let's simulate all possible moves into the future for multiple steps. Right, so for simplicity, let's just assume that we simulate. For simplicity, let's assume we only have two actions, left and right. This is where we are. And we simulate into the future for two steps, right? But you can imagine that you have hundreds of actions. So in this case, the tree branch will be, the number of branches in each node will be 100, right? And you can simulate it for 10 steps into the future. Okay, so for simplicity, let's assume we have two actions and we simulate it into future for two steps, right? So imagine this is, when we are playing this game, you're trying to simulate what will happen in the next, 5 steps or something, right? By considering all possible plays from both players. Okay, so we can simulate this tree, right? Because we know the dynamics. We know S, F, SA. So this is known, which means that at state S, we can simulate what would happen if we play that particular action, right? And then we can simulate what would happen if the second player tries that particular action, right? So we can just forward, imagine all the possible plays. So let's say we have two actions, we do 2-step planning into the future. So this is the partial tree we got. All right, so we don't want to keep growing the tree anymore because of the space or computation. So we just want to bottom up using our value network. So let's evaluate the value of those states at the leaf using our value network. All right, and now let's start doing dynamic programming from the bottom of the tree all the way to the root. Right, so once we evaluate the value at S prime and S double prime, let's propagate these values all the way to the root. Right? So the first thing we do is, so here you should think about this V hat S prime as the winning rate of the red player starting at S prime, right? Because this is the turn where the red node, the red player is trying to play. So what's the goal of the second player? So the second player is the blue player. So the blue player's goal is to minimize the winning rate of the red player, right? So which means the value at this node, the value at this blue node is actually the mean of the value of its two leaves, right? Because think about what a blue player would do here. So the blue player has two choices, left and right, right? And remember, the goal of the blue player is to minimize the value of the red player. So if you have two choices, of course, you will pick in an action such that the winning rate of the red player is minimized, right? So that's why the value on this blue node is mean over these two values, right? Because the blue player is trying to minimize the winning rate of the red players, right? So similarly, we can do the same thing for this subtree, right? And we're gonna do a mean over here as well. Again, the reason is that blue player is trying to minimize the winning rate, right? Now we can back up these two values, v left and v right, all the way to the root, right? Now the red player's goal is to maximize its winning rate, right? So now the red player has two choices, left and right. And of course, the red player is gonna pick in an action such that it has the highest winning rate, right? So in other words, the value at the root will be the max over the value left and the value right, right? Because again, the red player is maximizing the winning rate and the blue player is trying to minimize the winning rate of the red player, right? So, but this is just a dynamic programming, right? So you just, starting from a leaf, you do dynamic programming all the way up to the root. And you just need to be a little bit careful between this max and the mean, right? So you need to be a little bit careful about the role of each player here. But this is a classic dynamic programming for min-max, game. Okay, so if you do this evaluation, if you do this tree search for multiple steps and multiple layers, and you bottom up by the value network, and you basically bottom up dynamic programming, bottom up all the values all the way to the root. Now, for instance, this root says that you should pick this action, right? Because this action gives you the highest winning rate. So now this is the action you're going to play. Remember, you're currently at state S, right? So you're going to play this action. So this is the outcome of tree search, right? So you're trying to plan for multiple steps into the future, and you're going to bottom up using your value network prediction, right? Because you want to cut the depths of the search tree, because you might not be able to forward to do too many search tree, right? Because every step moving forward, we have 100 potential actions to evaluate, right? So we cannot grow the tree too deep. So we have to stop some level and trying to bottom up using our value network. Right? That's the purpose of the value network. Now you can imagine that if you have infinite computation resources, you can grow the tree all the way to the end of the game, right? So then you're just going to compute the minimax procedure, the optimal policy. That will be great, but that's not doable, right? So there's a trade-off between computation and the optimality.
So in a sense, the value network saves us the cost of evaluating our policy network to calculate the value at each of those leaves, right?
Yeah. Okay. So imagine your value network is actually equals to V star, right? So if that is the case, then we don't even need to grow out. We don't even need to plan into the future. We just needed to build a tree with depth 1, right? We just needed to evaluate different actions. That's it, right? But our V hat is not close to V star, probably at all, right? Because our V hat is approximating our policy gradient's output policy, right? So that's why we need non-trivial depths, non-trivial search depths into the future. I don't remember the exact number that they used in the paper, but we can all go and try to find it out. Okay, so that's the simplest tree search procedure you would use. So they're actually using something slightly more fancy, which is called Monte Carlo tree search. So this is the component that we haven't covered in our class, right? But this is more like, a topic in AI class. I don't know if your AI class covers this Monte Carlo tree search procedure, right? Because this has nothing to do with learning. It's just a search procedure, right? So let's quickly go through what this Monte Carlo tree search is. But in your mind, you should think about this approach as a more efficient and a practical version of the naive tree search procedure that we talked about from the previous slide. Right? So the idea is that you're going to maintain a tree. Right? Every node of the tree is the border position. Right? And the edge corresponds to the actions that you could pick at this border position. So imagine that at state, this is where we are, state. And let's try to select an action. So the way that you select the action is actually on every edge. So let me just write this. So on every edge, you have an estimate QSA, which you can think about this as an estimate of Q star SA. Okay, and plus something like 1 over square root N SA. So the second term is roughly equals to the bonus that we talked about in multi-arm bandit, right? So NSA is the number of times we tried SA. Right? So this is an exploration component in the sense that if there is an edge in this tree that we have not tried too many times, then the second term will dominate the first term, right? So this gives us some ability to try an edge that currently is underexplored. Of course, you want to do this, to keep a balance between the reward and the bonus, right? So this is just literally the up confidence bound stuff that we talked about, right? So the first component is the value. What's the game value if you were at state S and if you play action A? The second term is the bonus. That is roughly inversely proportional to the number of plays, the number of tries you have on this particular state action pair. Yes, question?
Aren't there like a lot of state action pairs? So like won't this N of SA be like very sparse or something?
Yeah, so this is a simulation step, right? So you're gonna do the simulation millions of times.
Oh, okay.
When you play the game, right? So this is not a real play. So this is, imagine you're playing against someone and you're at state S, right? Use all your computation powers to simulate this tree many times, millions of times, or even billions of times, right? So they're gonna simulate this on thousands of CPUs and hundreds of GPUs.
Okay.
So they're gonna simulate, like, imagine you're playing a game against someone. This is some calculation you do in your mind. Okay. And there's also expansion strategy. So once you get to a leaf, right? So we need to decide, if we want to grow that leaf, right? If we want to make that leaf as an internal node and keep growing the tree, right? So the way you do this is that if you have already visited that particular leaf enough times, above some threshold, predefined threshold, we're going to make that leaf to be a node, right? And we're going to create some children from that leaf. It's a very simple strategy. There's some hyperparameter you have to tune, of course. All right, and once we get to this leaf, right? As we said, we cannot keep growing the tree, right? Because there's a computation limit, right, and a space limit. So what you're going to do is actually bottom up using the value network. All right, so what the program actually did is that it first computes the value of this particular leaf, meaning you bottom up using this value network on that particular leaf. And the second thing that it did is actually play that PG policy, pi hat, starting from this leaf. Okay, so there's two procedures happening simultaneously, right? So one thread is computing V hat under the current leaf. Another thread is actually simulating a play using pi hat from this leaf, right? And once at the end of the simulation, you get a reward signal, right? And the way that they compute the value of that particular leaf is V hat S prime plus 1 minus lambda of the reward of this play. Right? So imagine you do two things in parallel, right? One thread is computing V hat, the predicted value at the current leaf, and another thread is actually simulating a play using your current policy gradient policy, your policy gradient output policy, pi hat, all the way to the end of terminate, all the way to the terminate state. And now what you do is just linear combine these two values together. So that's what they do for computing a value at a particular leaf. So this is slightly more advanced, than what we talked about in the previous slide, right? So you're actually evaluating a leaf using both the policy and the value network. Okay, so once we get this value, we can just using this dynamic programming strategy to backprop this value all the way to the root, right? So this is the backup procedure. So we get a value here, which is v hat s prime. Let's call this root leaf s prime plus r, right? So this is our value. Let's call it z. And then let's just backprop this z all the way to the root, right? So this is the path that we picked from this simulated play. So let's just increment the counts on each edge on this path by 1, right? Because we have already played that edge one more time in this simulation. And we also add this particular game value to the state action queue estimation. Right, so because we have already simulated that path, right? And we know that the value of that path. So let's just backprop the value all the way to the root through that trajectory that we traversed, right? Along the trajectories, we increment the count by 1 because we tried this state action pair, this edge one more time, right? In this simulation. And we also add the value, the current estimated game value to that state action edge value. Right? And then we repeat. So again, this is a simulation happening offline in a computation, right? When you're playing the game. So imagine you have a supercomputer and you just simulate that many times, right? Until you're satisfied about the property, the quality of this tree. And now you can, at the root level, you can pick an action that leads to the highest value of the game, the predicted value of the game. Right? So this is just a smarter way, a more incremental way to build the search tree. Right? And in the next step, you can reuse the search tree, right? Because you pick that action. Imagine at the end of the day, you pick this action, you get to this state. And you can just reuse this search tree, right? You just get you're just gonna use the subtree as a new search tree to start from. So in other words, you don't have to start from scratch. You just use the subtree as the warm start. And again, then do the simulation again. Right, so this allows you to use data, allows you to do data reuse across many time steps, and share statistics across different moves as well. But at the end of the day, this is just a more practical and incremental approach for the tree search procedure, right? And you're still using the value network to sort of cut the search steps. Okay, right? So this step is important. So you only go into a particular depth and then you bottom up everything using the value network estimation. Yes, question.
So in that rollout procedure, which policy is being used to simulate the opponent's moves? Yeah,
so the opponent will, so imagine you get here, right? So this is where you start and this is where you get, right? So the opponent will pick the max of so this is slightly complicated. I think notation-wise, I don't think they did a good job. So this is the opponent move.
Sorry, I meant in the picture number C. Like when you have that dotted arrow P pi.
Oh yeah. Okay. So they both play pi hat.
Okay, they both okay, but like V hat was estimating that trajectory, right? So yes. Why do we need V hat if we're doing this?
So you may So remember, we never be able to enumerate all the possible states, right? So what if in this particular play, this leaf, you never seen this leaf in the training data, even though you simulated 30 million games, but you probably haven't seen anything that's similar to this state, right? Mm-hmm. So for safety reason, let's just simulate pi hat for a full game, right? And then linearly combine these two predictions.
Okay, so like that leaf state might not have been there in the data set for the V hat?
Yeah.
Okay.
Yeah. Right? Because 30 million is nothing compared to the size of the game, right?
Yeah, but then why do we need the V hat? Like, isn't it just better to do this like simulation using pi hat just by itself?
No, because pi hat is a random policy. It has stochasticity, especially, right? So which means that if you really want to get an expectation, you have to simulate it many times, but you don't get that like time to do that in a real-time game playing. Right.
Oh,
so you're trading, you're doing this some trade-off, right? So v hat is approximating the expected value. But sometimes the prediction will be bad because you haven't seen that leaf in your training data, for instance, or haven't seen anything that looks similar to that leaf, right? So you want to add another safety guarantee so that you do a one, just roll out pi hat for one game.
So how is pi hat stochastic? Like, I thought.
So we parameterize it using stochastic and we do policy gradient, right? So no one can guarantee, at the end of the day, this is a deterministic policy, right? It might be very close to deterministic. That is true, but we can't really guarantee that it's deterministic, right?
Yep.
Okay, so this is purely their design choice, right? I'm sure they tried many choices. They tried v hat, they tried, roll out pi hat many times, but that's probably the best thing they could find in terms of the trade-off between computation and performance. Right. So there's a lot of design choices for this program. Like I'm sure they did pretty sophisticated evaluation of these different kind of strategies. Okay, so the bottom line here is that we enumerate and we plan for several steps into the future and we bottom up by a predicted outcome, right? So the predicted outcome helps us to cut the search depths of the tree, right? Okay, so that's basically the end. So, and the outcome of this combination of the search tree, policy, and value network is that program that actually can beat the legend of the game Go. Right? So as I said, they use extremely heavy computation. They have thousands of CPUs to simulate this Monte Carlo tree search. Right, and they also have hundreds of GPUs as well to help this search as well. And this all computations happening during the gameplay. Like literally, you're at this particular state, the program will actually just simulate this search tree. Right. So the policy, the value network, these things are pre-computed. Right. So these things are pre-computed before the game. Like you pre-compute v hat, pi hat, you frozen the parameters. Right? You store them in the computer, you ship them to Korea, right? So that's not going to change anymore during the gameplay. So what is happening inside during a game is this simulation, right? You can do search when you're playing the game, right? And you just use the pre-trained v hat and pi hat to help you cut the search space. And they also use this estimated value, this Q hat, QSA, to predict the winning rate. So if QSA is less than 0.1, meaning that if the predicted winning rate is less than 10%, I think the program will just give up. Right? So this quantity is actually, the quantity that's stored on the edge of this tree is actually the predicted winning rate that is being used for this program. Okay, so that's it, I think. So I think the only thing that we didn't really cover in this course is this Monte Carlo tree search. But as I said, as you can see, there's literally no learnings happening here, right? All you're doing is just some sort of smarter and practical search strategy. So this is more like a traditional AI stuff. But I think AlphaGo is a very nice example of combining traditional search approach from AI literature and modern machine learning and reinforcement learning approach. Right. So for games like chess, you probably don't need too much machine learning because the search space is okay, especially under the current computation resources we have. Right. But Go, we have to use function approximation. We have to use modern machine learning approach to generalize. And simultaneously, we still need to leverage the power of search, right? In order to get a really, really strong program. So I think this is a really nice example of showing the power of combining techniques we developed in AI and techniques we developed in machine learning. Okay, so let's just quickly summarize what we talked about, right? So we started talking about this behavior cloning approach. So we just simulate this behavior cloning on 30 million expert data set. And then we do classical policy gradient on self-play. Right? So policy gradient wise, this is just a policy gradient from reinforce. I think the only non-trivial thing is probably this self-play and this fictitious play strategy. Right? And then the third step is just least square. Right? You just play the policy trained from the policy gradient procedure 30 million times, get 30 million state game value pairs, and minimize the least square training loss on that data set. Right? And the last step is to use the pre-trained policy and the pre-trained value network together with a search tree to further improve the performance of your strategy. Right? So your strategy at the end of the day is a combination of a search tree, a partial search tree, a value network, and a policy. Right? So that really makes the program really strong in order to beat these human champions. Now, later on, they released another paper, another Nature paper, which is AlphaGo 0, which is a later version that get rid of the imitation learning component. So they were not happy about initializing from human plays. Because at the end of the day, it seems that what we understand about this game is probably some suboptimal. So if you initialize your policy using plays from human, it probably gonna make the policy gradient parameters to be stuck in some local minimum. Right? So in the later version, they get rid of this step. They just start from scratch. Right? And they have some new algorithm advancement in the new paper as well. But I think at this stage, you actually will be able to understand what they're talking about in that Nature paper. Like I actually encourage you to actually download that paper and read that. And you will see actually what we covered in this lecture. I mean, they're using this stuff in their papers. Okay, so I think that's the end of today's lecture.